All right, good evening. My name is Hunter, and this is content review for Gen Chem students. This week we're going over electrochemistry, and it's electrochemistry because we are tracking the movement of electrons in these reaction cells. Today we're just going to be dealing with galvanic cells, so they're all spontaneous reactions, and it's a mercifully short uh, worksheet today. So with that, let's go ahead and dive right into it. Identify each half reaction below as either oxidation or reduction. So I've written a little mnemonic up here, and that is oil rig. You may also have heard Leo Gur, and this is just a simple way of keeping track of where oxidation and reduction are happening in these half reactions. Um, Oxidation is loss of electrons, and reduction is gain of electrons. Um, whatever mnemonic you use is great. Um, we'll have another one a little bit later, but galvanic cells, electrolytic cells, galvanic cells are super useful. They're in batteries. I've used them for electroplating um, metals onto other metals. So nickel plating, gold plating, processes like that all use galvanic cells. And a lot of biochemical reactions are reduction oxidation reactions. And so being familiar and being able to track these things is really important. We're going to be doing a lot of accounting steps, and that is because it is not enough to, try and do the pattern recognition thing and go, okay, we have a positive charge on the left here, that must be oxidation, and oh, we have a positive charge on the other side, that must be reduction. That's not the case. And we're going to go into why. So I'm going to zoom out just a little bit, make sure we still got that in view. We do. Okay, so identify each half reaction below as either oxidation or reduction. So looking at A, we have chloride with its negative charge and dichloride, diatomic chlorine. What we need to remember about diatomic species like chlorine is that in their diatomic state, they have a charge of 0. Um, Chlorine ions, if we need to pull up our periodic table, it's 1 off from the nearest noble gas, and so it has that 1 negative charge. It wants to get rid of that to get its noble gas configuration. So that's where that negative charge comes from. So as an accounting step, we have a -1 charge on this, but there's 2 over here. So we're going to throw our coefficient up there, multiply that by 2. So we have a total charge of -2 on that chloride side of the reaction, or half reaction. And 0 times anything is 0. So the way to think about this is we have a -2 net charge on the left side of this and 0 on the right. We need to add electrons to the side with the more positive charge. And so we're going to add our 2 electrons to the right side of this reaction in order to balance this. And this is just our accounting step. So we're adding electrons to the right side. That means that this is a loss of electrons from the chloride ion side. So this would be a oxidation reaction, and that is because chloride is losing electrons when it bonds with a pair into a pair, and it is oxidized. All right, let's look at another example. Here we have magnesium. Magnesium? No. Uh, Magnesium is Mg. What are you? Manganese. Manganese with its +2 charge. And we can just get rid of the oxygens here. We don't really need to consider them, but we do need to figure out what charge the manganese is going to have on the other side of this reaction. So looking at oxygen, if we pull down our periodic table, I should actually do that. Oxygen is 2 over from the nearest noble gas, so it has that configuration of -2. Yeah, it has that configuration of -2. Go away. There's 2 of them, and so the manganese is going to have a 4 positive charge to counterbalance the 4 negative charge resulting from those 2 oxygens that it's bound to. So in this case, we have a 4 positive charge on the right, a 2 positive charge on the left. Let's go ahead and write that. We need to add electrons to the right side of this in order to balance that charge. And so this also is an oxidation. Manganese 2 plus is giving up electrons when it binds to those 2 oxygens. And so this is an oxidation reaction. Looking at C, we have diatomic hydrogen, so that has its charge of 0. Going to hydrogen by itself, let's go ahead and get our coefficient on there ahead of time because we know we're going to need to. So that's 2 times positive 1 and 0. So we have a net positive charge. We know we need to add 2 electrons to the right side of this in order to even out that charge. Make sure you can see that. This is also an oxidation reaction. All right, let's look at our nitrate. And again, we don't really need to worry too much about the oxygens except for accounting for how much um, positive charge the other species has to balance it out. So if we split this up, we have nitrogen and we have 3 oxygens. Each of those has a -2 charge. There's 3 of them, so we're going to have -6. The whole ion has a -1 charge, and so x minus 6 will equal -1. So this must be 5. So that gives us, I'll just do it down here. So we have nitrogen plus 5. Continuing to nitrogen, there's only 1 oxygen, which would normally have a -2, so this must be +2. So in this case, I'm going to move this over. In this case, we would need to add 3 electrons to the reactant side of this reaction in order to balance out these charges. And so because this represents a gain of electrons, nitrogen is gaining 3 electrons. This is a reduction. Cool. So again, you may be tempted to just look at which side the charge is on and whether it's positive or negative and go, oh, well, this must be a reduction because there's a gain in charge or there's a loss in. It's not how it works. Do these accounting steps. All right, moving on to galvanic cells. Again, these are all spontaneous by definition, and I've pre-done this this cell notation here. You have your um, anode on the left. This is the species. This is the site of oxidation. So anox and a red cat is your mnemonic for remembering that. Um, Anode is the site of oxidation. Cathode is the site of reduction. And we're given this notation. We need to, assuming the schematics below represent galvanic cells as written, identify the half cell reactions occurring in each. Okay, cool. Where do I want to do this? Let's look at A, do it right here. So we start with, now we're working with magnesium. We have magnesium solid. 1 bar in between it just means that that's making up part of a half reaction. Aqueous, that has a 2 positive charge on it. And to balance out those charges, we would simply add electrons to the product side of this. So that would make this oxidation. Oxidation is loss of electrons. Magnesium is losing electrons. And then we have copper, aqueous, with a 2 positive charge, to copper solid. And the reverse is true. So we need 2 electrons on this side to counteract that 2 positive charge. This is the site of reduction. Now, there's another step here. So we're going to add these 2 half reactions together. The electrons on both sides cancel out. So we have magnesium solid plus aqueous copper with its 2 positive charge forms aqueous magnesium with its 2 positive charge and solid copper. Your charges need to cancel out, or yes, your charges need to balance out and your electrons need to cancel out. So there will be cases where you need to do some additional stoichiometry here. Move that out of the way. We'll do B right here. All right. Yeah, we'll do it this way. So we have solid nickel to aqueous nickel. Pretty straightforward, need 2 electrons on that side. We then have silver, aqueous to silver solid. There's only a single positive charge on this silver, so we need to add 1 electron. And if that's as far as we had to go, we could be done there, but we're not quite done. We need to add up these half reactions. So because we have 2 electrons up here, we need 2 electrons on the bottom or in the other half reaction to be able to cancel this out. So we're just going to add a stoichiometric coefficient to each of these species. You could just as easily have written it like so, but I'm going to put it on each species so that it's abundantly clear. 2 electrons cancel out. You have 2 silver plus solid nickel, 2 solid silver, again, this was aqueous, plus nickel 2 plus aqueous. And that is your balanced half reaction. From the information provided, use cell notation to describe the following systems. So we're basically writing what was given to us up here. And again, I have this off to the side just for our reference, but we might not need it. So we have a 1/2 cell solution of platinum nitrate forms platinum metal, while in the other half cell, copper metal goes into copper nitrate solution with all solute concentrations of 1 molar. And we do need to make a note of those concentrations in our notation here. So I'm going to write the balanced equation here first, just because I think it will help. We're told that this is in solution, excuse me, and that it forms solid platinum metal. These species split up. Nitrate has a -1 charge associated with it always. There's two of them. And so we can infer from that that our platinum ions, cations in this case, are 2 positive each. So we've got the first half here. Platinum 2 positive to platinum solid. We're gaining electrons, oxidation, excuse me. Oxidation is loss. Yes, okay. I just had it labeled incorrectly in my answer key, but I wrote it in the correct order. So we're good to move forward. All right, so similar, we have copper metal forming copper nitrate. Again, those split. Nitrate always has a -1 charge associated with it, and there's two of them, so our copper must have a +2 charge associated with it. So we have copper solid forming aqueous copper cations with a 2 positive charge. And this is our oxidation. So now to write this entire thing in cell notation, we have copper solid, vertical bar, copper aqueous, 2 plus, and 1 molar. Make it a little bit more on the same level. 1 molar, double bar. Oxidation is the anode. And then aqueous platinum, 2 plus. And our concentration there was 1 molar as well, comma, 1 molar, forming solid platinum. And we're done. Cool. This is our last exercise. It's the same thing. We have one half cell consists of silver electrode in a 1 molar silver nitrate solution, and the other half cell a copper electrode in 1 molar copper nitrate. It's oxidized. So they're telling you which one is your anode right away. Anox. Excuse me. So we know that copper, and we've already done this one up above, so I'm not going to repeat it, but this is our cathode, excuse me, our anode, site of oxidation. Now we just need to figure out the silver electrode in solution. So there's our silver solid. This breaks up. Nitrate always has a -1 charge associated with it, so our silver cations have a +1 charge associated with them. And so our silver aqueous, 1 molar, +1 charge, forming silver solid. Excuse you. And that is our final answer. Again, short and sweet one this week. get out and enjoy the nice weather. If you have an opportunity, take a nap. And I will see you next week.